Good morning, everyone. We're going to get started back here in Chapter 5 this morning. I hope midterm 2 went well for everyone. We still have a few exams ongoing this week. So like midterm 1, you probably won't see scores. Maybe by Friday we'll get them in. Sometimes we can get scores posted by Friday. If not, usually by the following Monday. And then usually you can see your exam towards the end of that next week to check your answers. We'll have a few things more to say about midterm scores and how to interpret your grade and situation in the class probably on Friday. So I have a few more things to say about how to interpret scores and how to think about how you're doing in the course later this week. So let's get back into this topic of energy. So Chapter 5 is about the energy changes that accompany reactions. We see that from last time we had delta E is like the energy change of the reaction. And then we could also see that the reaction could either absorb or release heat, or it could do or receive work. So work can be done by the reaction on the surroundings, or the surroundings can do work on the reaction. So we'll try to get a sense here today what it means for a reaction to do work or to have work done on it. So we'll try to look at what that actually means physically today. But in the terms of just solving this problem, it comes down to an equation that looks like this. Delta E is equal to Q plus W. Now there's a tricky part of interpreting this equation is we have to keep kind of straight what this delta E, Q, and W are with respect to. This is the delta E usually with respect to the reaction, the Q with respect to the reaction, the W with respect to the reaction. So it's like the energy change of the reaction, what is the heat change of the reaction, what is the work change or the work difference by the reaction. So we get this equation delta E is equal to Q plus W. Now reaction is often called system. So if we say system, that's really the same idea as reaction. So if you see system, that's really just a synonym or just what we think of as being a chemical reaction. So the system is often that reaction. And then you can also have a slightly different, it's the same equation. I'm going to rewrite it. But you can also have this with the perspective of the surroundings. Then everything kind of flips, So like if a reaction absorbs energy, if delta E is positive for the reaction, then that energy had to come from the surroundings. So the delta E of the surroundings would be the exact value, but negative. And so the delta E of the system or the reaction is just negative the delta E of the surroundings. So just they have opposite signs of each other. Same thing with Q and W. So if Q of a reaction is the negative Q of the surroundings, the W of the reaction is the negative W of the surroundings. I'm not saying one is negative, the other is positive. I'm just saying if one of them has one sign, the other has the opposite sign. So if a reaction releases heat, so reaction releases heat, so its heat drops. Where did the heat go? The heat goes to the surroundings. So the Q of the surroundings would be positive. But anyways, one of the other parts of a problem like this, it's kind of a silly problem in a way. It's just like somebody came up with this problem so we could just throw numbers in and calculate, well, what is a delta E given a Q and W? But it's really the interpretation of the sign. So interpreting what the sign of Q is, what the sign of W is from the words in the problem is kind of the tricky part or the sort of idea of this question. And so it's a delta E of the reaction. So we're looking at this question here using the perspective of the reaction. And so then the delta E we're going to calculate for our reaction would be the Q reaction. Now a reaction that absorbs 22 kilojoules of heat, absorbing heat is upward. So the Q of the reaction is positive. And so the Q of the reaction would be plus 22 kJs. And then the W of the reaction, from what we're told, that it does 45 kilojoules of work on the surroundings. Doing work on the surroundings is negative. That's negative work. And so the W of the reaction here is going to be negative 45 kilojoules. The next slide will try to show us what that means, or like what it means to have work done on the surroundings or have work done on the system by the surroundings. So we'll try to get a picture on the next slide of what a physical picture might look like for doing work. But doing work on the surroundings is moving the surroundings. So like physically moving the surroundings takes energy. Like heating the surroundings takes heat away. So if I want to heat up my surroundings, I have to lose heat from the perspective of the reaction. So for a reaction to heat up the surroundings, think of a combustion reaction. Burning methane, like on a stove, that's an exothermic reaction. That's a word we'll see later, but that reaction releases heat. So the reaction drops in heat so that the heat can go to the pot of water to heat it up. So the reaction loses heat so the surroundings, the water pot, can be heated up and gain the heat. So absorbing heat, positive, but then the same thought would be, if I'm going to heat up my surroundings is negative Q for the reaction's perspective, then moving the surroundings is going to be negative work from the reaction's perspective. It's going to take energy in the form of work to move an object. And so doing work is moving things, and so that's where we get the sign negative here, is just doing work on the surroundings. We have to interpret that as being negative in terms of the sign of W. And so the delta E is just simply plus 22 kJs for Q, and then plus the negative 45 kilojoules for the work. And so that net delta E would be minus 23 kilojoules. So whatever the system or process is, has 23 kilojoules of energy that can be released, and it can be released by any combination of Q and W. So Q, if we change the way this reaction or system's carried out, maybe we could get Q to be 24 kilojoules, but then W would have to adjust accordingly. I can't do math quickly in my head, but that would make Q have to be negative 43 kilojoules. So the sum of Q and W has to be whatever the delta E for a system is. So delta E is like a constant for a particular system or reaction. And Q and W can take on whatever values they want so long as they sum up to the delta E. So systems can change depending on how we carry a reaction out, or depending on the type of system it's in. Q and W can have different values, but their sum has to go to whatever delta E is. That's another topic we'll keep coming back to on a couple slides this morning, on the difference between state functions. So this is our state function, and then Q and W are our non-state functions. So non-state functions, Q and W, the state function, the delta E. And that just means path dependent. So path independent state function doesn't depend on how we carry the reactions out. Delta E is a constant. Q and W can vary depending on the type of system or how the reaction is being carried out. Okay, just spending a little bit of time on this problem just to try to summarize a few things we were talking about last time. I know the early part of chapter 5 is pretty confusing because it gets into a lot of big ideas that we kind of cursory take a look at just through pictures or through ideas and thoughts that then later we're going to see in the chapter that we lead towards some fairly ordinary equations and problems that we can solve with these ideas. We're just trying to understand the difference between like energy in the form of heat and energy in the form of motion is kind of what we're trying to talk about here in the early part of chapter 5. Now this slide here is trying to get at what it means to move the surroundings. So we see kind of our initial state here. So the before is on the left, and we just have some sort of a container that has some sort of a volume. Maybe there's a chemical reaction that's going to take place inside this container. So let's say we then have some chemical reaction or some system take place where a change occurs, and then that change leads the volume to expanding in that sort of container. You can think this might be a piston. This could be like a combustion reaction occurring in a car. So then the piston expands, and so you get the expansion. And now that expansion is physically moving the surroundings. So to move this piston, like this is just meant to show like atmospheric pressure pressing on the piston. But the motion of the piston's going upward. We're physically moving the surroundings. We have to put the surroundings into motion. And we mentioned moving the surroundings is negative work. And so the system does work. Work has a negative sign. Work turns out to be equal to pressure times delta volume. Now, that's not something we're going to throw a lot of numbers into. Probably we won't throw any numbers into that ever in terms of like actually solving work numerically with certain pressures and volumes. We actually don't know a whole lot yet in this class. Like we'll introduce, pressure volume calculations in chapter 10 later. So there's not a lot of sort of ideas that we know yet into how to solve a problem throwing numbers into this, but we're really just seeing that negative sign, that work is negative when we physically increase the volume. So we increase the volume, that leads to expansion. So expansion is negative W. So expansions of gases have a negative W. W, another way of putting that would be probably better put, W is less than 0. So W is negative whenever we have expansion. Now expansion can occur when a reaction leads to an increase in the number of gas moles. So N's the symbol for moles, gas for the, so whenever we have a reaction takes place that leads to the formation of gas, we have more gas formed on the product side of the reaction than on the reactant side. So we can say that that's the change in the moles of gas during a reaction. So we increase the number of moles of gas in a reaction. Most combustion reactions fit this category because most combustion reactions start with like a hydrocarbon, O2, turn it into a bunch of CO2 and water, usually because you have a flame taking place. Usually your products are gases. So if most combustion reactions do this, have this kind of characteristic. So most combustion reactions lead to an increase in the gas moles, which leads to expansion, and that allows those reactions to, on top of the temperature that they'll increase by, that'll also increase the volume. So there's other factors than just the gas moles, but a reaction generally that increases in the gas moles will lead to a negative work and a reaction that's capable of doing work on the surroundings due to the increase in the volume of gas occupied by the new gas moles. And then the opposite happens, we get contraction. If you think of an initial state being big volume, final state being low volume, that would be the consumption of gas. If we consume gas in a reaction, if the change in gas moles is less than 0, if that's negative, if we lose gas moles during the reaction, then that should lead to contraction. And the contraction would have a W greater than 0. So the physical picture of the surroundings working on a system is just the surroundings collapsing. So like a contraction event, a consuming of gas moles is what you can think of as being something that is the mechanism or the way that the surroundings works on a system. It could literally be you pushing down on a piston. That would be you working on the system. So you would be taking your energy to press down on the piston. You would be expending energy that would go into increasing the pressure in that sort of container and decreasing that volume. So you would be the one expending work so that energy would be absorbed by that system in that event. Okay, so expansion, negative work, because we're moving the surroundings. The surroundings moves inward due to contraction. Absorbing gas moles is a way we can consider work being positive. So I just wanted to give you a mental picture, an idea of what it looks like to do work, moving the surroundings, negative work, and then the surroundings moving inward on the reaction, contraction being work positive. Okay, let's look at a couple problems, because usually the problems on this topic will just give you a few words like this. We have a balloon that's warmed up and it expands. So then we're being asked to interpret the sign of Q and W for the air molecules inside the balloon. So you have a balloon, initially whatever volume, and then the temperature is going to increase, the volume is going to expand. So did the air molecules, did they receive work or did they do work? And then did the heat increase or decrease for those molecules? What do you guys think? Think about this for 30 or 60 seconds. You can chat with your neighbors if you want, compare answers. So what do you guys think here? I mean, I've already written, so the temperature increases. Temperature is heat. So the air is what we're looking at as our system. So this is an example of a system that's really not a chemical reaction. The system is just the air. And so the air being our system went from a lower temperature to a higher temperature. So that means the air had to absorb heat. So air absorbed heat. Absorbing heat is Q positive. So air had to absorb heat. Heat had to be positive. And then what about work? So the balloon expanded. What's the sign of work? Is that negative or positive? That would be negative. And so the sign of work for expansion would be negative. So we'd be at answer C here. So if you had answer C, that's good. Now, when we throw in the concept of reactions, it's going to be a little bit trickier. So when we start thinking of a reaction taking place, we're going to have to be a little bit thoughtful of, well, what's the system? What's the surrounding temperature? We'll see an example of a reaction and its temperature changes in, I think, on the very next slide or 2 slides from now. Let's talk about systems a little bit, because this will help us get into how we go from energy into enthalpy. If you know or have heard what enthalpy is, they're somewhat similar to each other. But before we get there, let's talk about some different type of systems so we can understand how we will eventually define and sort of relate enthalpy and kind of see its connection to energy. So an open system is a container at constant pressure. So this would just be like a beaker, let's say. And so you have some reaction taking place in a container. If a gas is generated, it can float away. So we can lose matter, to the surroundings. We can gain matter from the surroundings. So we could have, oxygen absorbed in from air. If we release a gas, it would float off into the atmosphere. There's no way we can increase the pressure of this system because the gas would just float away from the container. It's not sealed in, so the pressure has to be constant. So an open container can't increase its pressure due to being open to the atmosphere. And they can also absorb heat with the surroundings, so we can absorb, heat to and from the surroundings and matter. Now, absorbing heat means that if the reaction takes place that causes the temperature of that solution and beaker to get hot, then the heat's going to be released to the surroundings and eventually cool back down. And then if we cause a reaction that cools down, if we have a reaction that takes place and the beaker turns cold, then the heat will be absorbed from the surroundings and eventually warm that container up, and it'll go back to room temperature after however long it takes. So an open system just can exchange matter and heat with its surroundings, can't increase its pressure. That's why we call the open system a system at constant pressure. If we then just take that system and close it in, so if I take that system here where I have some reaction taking place, and then I just simply put a lid on it and seal it up, then that system can increase in pressure. So here we can't exchange matter with our surroundings. So if the reaction generates a gas, the inside of the container is going to increase in pressure. These types of systems can be dangerous to work with in the lab because if you generate too much gas, the thing can explode. So sometimes, or if you are sealing in systems, you have to be careful in the laboratory, so you often don't do this. But the system can exchange heat with the surroundings still. So you can still have heat exchange. So you can still have a reaction that gets hot, and if it gets hot, it leaks the heat out to the surroundings. In fact, when a system is in a container, the walls of the container are usually the surroundings. And usually the water, if you have a reaction taking place in solution, usually the solvent is the surroundings. So, think of your container in both of these and all these systems, the container and the solvent are the surroundings. That'll help us later when we start putting a thermometer. If I put a thermometer into the reaction mixture, it's really not touching the reaction, it's touching the surroundings of the reaction. So the thermometer is also the surroundings of the reaction. So almost anything you touch relative to a chemical reaction in a system, you're the surroundings of that reaction. The thermometer, the container, everything that is touched by what was there versus what is there, which is the reaction. We mentioned this before. It's hard to touch the reaction because it really isn't a thing. It's just a concept. It's just what was there compared to what is there. And so what you can touch is what the before and after are in contact with. You can be in contact with the surroundings. Okay, and so then if you take a closed system and then put it in like an insulated environment. So imagine you just take this closed system, some reaction taking place in this system, and then you just simply insulate the container. Then that just becomes a system that can't exchange heat or matter with its surroundings. It's really not all that interesting. Not quite sure why the book even mentions this system. There's not a whole lot to do with this system, because if you put like a thermometer, outside the system, you're not going to pick up any change because there's no heat or matter being exchanged from the system. So an isolated system would be one at constant volume in an insulated cup, so that the inside of the container can still get hot or cold. So maybe the idea of this system is if you generate a heat, then the inside of the container would stay hot and not cool back down because it can't exchange heat with its outer surroundings. And then if you do a reaction where it gets cold, it stays cold. So maybe this system is nice because if you could put a thermometer inside of here, you can get a initial and final temperature that would be both very constant. So maybe we'll use the idea of this system as we go for calculating the change initially to finally for a system. So a lot of times we'll do reactions in a closed system that we assume is an isolated system, so that you can get a good measure of what was the temperature before, what was the temperature after, without kind of dealing with the fact, hey, wait a minute, if I do a reaction in a cup, it's going to get hot and then eventually cool back down. It's hard to really get a measure of temperature changes when we do things called calorimetry. So when we get to calorimetry, I think we'll be kind of assuming or considering systems as if they're isolated. Maybe this will make sense later. But for now, just kind of have the idea that an open system can exchange matter, can't increase its pressure. The closed system can increase its pressure. It's at constant volume. So if we generate a gas, the pressure is going to go up. If we consume a gas, the pressure is going to go down. Now, one other thought is that, well, what happens to work? What happens to the concept of being able to move the surroundings in these systems? And so the open pressure system, we're going to see it's going to be hard for it to move the surroundings without being sealed in. So the open system, work is going to be essentially like negligible. So work will be essentially net zero. We'll show on the next slide how that is for the open system. So it's hard to move the surroundings in an open system because it just flows through the surroundings. We can't really move the surroundings in that case. And then work becomes close to zero. I don't know how to put this. Work is not entirely zero, but it's close to zero in the closed system. So work is almost negligible in the closed system, such that usually we ignore it anyways. Where work becomes a significant quantity, like if you look at that example we did to start class today, work is only a large value in a system not even shown here. That would be a mechanical system, like an engine. So a mechanical system is one where work is going to be entirely like something you have to account for. Chemical systems, work is either going to like reduce itself to zero in the open system or be so small we ignore it. So let's say work is small in the closed system, so small that often we ignore it. And so when is work not small? Mechanical systems. And then this is a chemistry class, not a mechanical engineering class. So we're going to mostly, even though we spent a lot of work trying to understand work, we're going to eventually get rid of it and just talk about heat changes. And so all of this energy we're expending to try to understand the concept of work is going to kind of just be for the sake of understanding what it is, and then we can understand why we're ignoring it. It's because the systems we're working with in a chemistry class are such that it's either zero or so small that it's negligible. Okay, so with all that, this slide here, gory slide, let's try to work through this. So the idea of enthalpy versus energy is what this slide is trying to show us. So enthalpy from a physics standpoint is the energy of a gas plus its pressure times its volume. That's just the fundamental definition of enthalpy versus energy. So you can see H and E, enthalpy is H, very, very similar to E, but not exactly the same. And so then if we say, well, a change, usually we're looking at for a reaction of like A to B, what is the change or what is the delta H? The delta H, of course, would be whatever the enthalpy is of B minus the enthalpy of A, just to introduce the idea of change and enthalpy. It would be the same idea. The change of energy would be whatever the energy is of B minus the energy of A. So just final minus initials are delta. And so our delta H would be the change of, the energy plus the PV for the products minus the energy plus the PV for the reactants. So there'll be the delta E plus should be the change of that enthalpy before and after the reaction. And so then if we then put the delta through the equation, we get delta E. And then if we're at constant pressure, then it works down to P delta V, just because pressure can't change. So instead of delta PV, it would be P delta V. And then that's where we can say, oh, wait a minute, work is related to PV. Work is negative P delta V from that equation a couple slides back. And so that would mean negative work is plus P delta V. So I can put negative work into the equation here. And so if I write that, I get delta H is equal to delta H is equal to delta E minus W. So we see work kind of like incorporated into this equation. And so delta H and delta E are fundamentally related just by the difference of the work that the reaction can do or have done on it. And so then we can recall that delta E is Q plus W. And so if delta E is Q plus W, I throw Q plus W in the place of E here, and then you can see that Q plus W minus W, W just annihilated itself. So it's not that the W of the reaction is necessarily zero, it's just for the open system, it's incapable of doing work on the surroundings. It can't do net work. So even if a reaction generates a gas, that gas can't work on the surroundings because it can't increase the pressure of the surroundings. It can't physically move the surroundings. And so work goes away in our equation here, and enthalpy becomes just the heat change of that process. So the little symbol P here just means at constant pressure. So delta H, the enthalpy change of a reaction, is the heat change of the reaction occurring in an open system. Now, if you enclose the system, then all of this breaks down, and we're not going to go through the math and show what work is in that case, but it's so negligible that even for the system at constant volume, that we will assume that it's so close, like the Q of the constant volume system, because work is so small for a chemical system at constant volume, that delta H is approximately equal to QV, and this would be for the chemical closed system. So the closed system's at constant volume. And then by chemical system, I'm just saying, well, this wouldn't be the case for a mechanical system at constant volume. That would be a whole different story, but this is a chemistry class, not a mechanical engineering class. So chemical system, a container just sealed in, the heat change is approximately delta H, and for the open system, it's exactly equal to delta H. And so the delta H of reaction, the delta H here is the heat gained or lost at constant pressure. Delta H is, we often call it the heat of reaction. So you'll see us call delta H, think of H for heat, and then it's equal to the heat change taking place for the reaction. Now let's think about exothermic versus endothermic, and that reactions can be spontaneous with either. So the sign of delta H isn't telling you if the reaction can or can't take place. For example, we see here calcium chloride solid being absorbed or thrown into water. We know by the solubility rules that that ionic compound should dissolve in water because it's not one of the insoluble exceptions for chloride. The same thing with ammonium nitrate, that this should dissolve in water. But they have opposite signs of delta H. One of them is negative, one of them is positive, but we know both of those reactions should take place spontaneously. Spontaneously means without any external force. Like I should just be able to pour water onto both those salts, have them dissolve, and then have a heat change. Now, which one do you think will heat up the water? Do you think it'll be the calcium chloride? If I add water to calcium chloride, do you think the water will get hotter or colder? Do you think that it'll feel like hot or cold? And then the ammonium nitrate, do you think that'll feel hot or cold if we add water to it? So who thinks if I add water to calcium chloride, the water should feel colder? Anybody want to volunteer? Usually nobody wants to volunteer because I feel like it's a trick question. Does anybody feel like if I add water to calcium chloride, it'll get hotter? Yeah, it should get hotter because what we're going to see is that the calcium chloride loses heat, the heat goes into the water, heats it up. And then the opposite should take place for the ammonium nitrate, that the reaction absorbs heat, but where did the heat come from? The heat will come from the water's heat. It'll take the heat away, it'll take temperature away from water, it'll lower its temperature. So let's do here. I could pass these around, but I'll just leave these up front. Maybe I'll mix one at the end of class if nobody really cares. I think you've all experienced hot and cold packs. But what I have here is this is the ammonium nitrate. And it just says, well, this could be the hot or cold. But so hopefully we'll see that this is the cold pack. And so I just have some beakers of water. I also have thermometer probes. So I'm going to check the temperature of water. So my water temperature is about 20.3. It's going up a little bit. 20.3 degrees. Does anybody want to be a helper and come read the temperatures? Just show up online. Does anybody want to come up here? Nobody wants to come up. Okay, that's fine. I don't think you think I'm lying to you. So 20.3 degree water. I'm going to add it to the solid. Now you're not going to see all the solid dissolve. I'm going to feel it. It's cold. And so then I can put a thermometer probe in the water. I'm already at negative like 3 degrees. So you can feel, I mean, like I said, you felt cold packs before, but you're seeing it's the endothermic reaction. It's a reaction that has to, it's either leaking or it's already absorbing moisture out of the air, or a static with the thermometer leaking it. So anyways, I made a cold pack with ammonium nitrate because it's absorbing heat. It's taking my heat away when I touch it. That's why it feels cold. Okay. So the endothermic reaction absorbs heat from the surroundings. And then if we go back to hopefully room temperature water, the thermometer probe has to warm up a little bit. So we're going back to 20 degrees. So this room temperature water, so no funny business with water. Now I have a different solid. This is calcium chloride. We all leave it for a double wrap. So I add the water. You'll tolerate it. Very, very fast reaction. Like these compounds, when they're soluble in water, it's pretty quick. I'm already at 47 degrees. I'm at 47 degrees. I was at 50 already. Too exciting. And so that's our exothermic reaction. Now the sign of delta H, negative, is implying that the reaction released heat. Where did the heat go? Well, heat's going to you when you are in contact with that reaction. It's not that shocking. But if you care, you can check those out after class. I can mix together a fresh pack later if anybody wants to check that out. But again, calcium chloride, the temperature of the surroundings, that's the key, is that we're the surroundings. So the temperature of the surroundings increases with the exothermic reaction. So this is the exothermic. The reaction releases heat, so the Q reaction's negative. It's less than 0. So if the Q reaction is less than 0, what's the Q surroundings? Q surroundings is greater than 0. That opposite sign, hence the temperature of the surroundings increases. And then we saw with the ammonium nitrate, the opposite, the Q reaction is positive. That's what delta H means. Delta H is the Q. So the Q reaction positive. So the temperature or the Q of the surroundings is less than 0. So the temperature of the surroundings drops quite quickly. So we were at negative, temperatures below 0 in Celsius, very quickly upon ammonium nitrate dissolving. Okay, so a couple keys here that we see the difference between exothermic and endothermic reactions, and that they can both occur spontaneously. So the sign of delta H isn't compelling one reaction to occur and the other not to occur. That's what delta G is. When you learn that later, delta G is the equation that if you know delta G is negative, then a reaction can occur. If you know delta G is positive, then it shouldn't take place. It should be a non-spontaneous process. But that's a topic for chapter 19 in Chem 1220 that you'll see later. Maybe you learned about it, I don't know. But so the idea here, the sign of delta H does not tell you if a reaction can or can't take place. So both these reactions occur at room temperature, and then they cause a temperature change accordingly. We also can relate the ideas of enthalpy and energy to back to the state function idea. So let's come back to the idea of delta H is a state function, just like delta E is a state function. Let's try to talk again about why that is. And so the idea is picture a charged battery. So a battery has a full charge, and a full charge battery has either so much heat it could use or get out of it to warm up something. So you can use the battery to maybe warm up a heating element. So all the energy the battery has goes into heating up an object. Or you can use the battery to run a fan. So you can use the charged battery to operate a fan, in which case the fan blades and the motor are going to get hot, but then mostly do work to move the fan blades. So we're going to have the energy of the battery go into some amount of work done to move the fan, and then some invariable heat that's caused by the process of the motion. And so the sum of heat and work has to go and add up to whatever the energy that's discharged by the battery is. So the amount of energy that the charged battery has is a constant. But the amount of heat or work that we get out of the battery just depends if we're heating something up or using a fan or some combination of the two. So Q and W can really be anything so long as they add up appropriately to the delta E. The delta E or the delta H is what is the constant. So the energy lost by the battery is just a value that is path independent. Doesn't matter on how we're using the battery. So delta H, delta E, the distance between 2 points, those are state functions. Non-state functions are things like heat, work individually relative to each other. The total distance traveled by an object is also something that's a non-state function. That was the example of the distance between here and Cleveland's a constant, but your path to get there, it depends on how you get there. The sum of Q and W is delta E, so the sum of heat and work for a process are a state function, but individually Q can be anything, W can be anything, hence that's why they're non-state functions. Okay, let's come back to the idea of then temperature changes, interpreting Q and W signs, because I mentioned earlier, like the difference between the balloon with air versus a solution. It gets a little bit trickier because we just have to think frame of reference. So when delta H gas is added to water, the solution temperature rises. And so now the solution temperature, is that the reaction or is that the surroundings? That's of course the surroundings. So the temperature of the surroundings is increasing from what we're told here. And then we can infer what the reaction's heat had to undergo in order to cause the temperature of the surroundings to increase. So is the dissolution of HCl exothermic or endothermic? And then what's the sign of delta H? So again, take 30, 60 seconds, see if you can come up with the answer. Feel free to compare with your neighbors. Does anybody think it's D? I feel like you guys know the first one I go to is the wrong one usually. Anybody think it's B? Oh, I was right there. No, B is wrong. So anybody think it's A? There it is. I thought I was tricking you guys again, but no, it is A. So exothermic. Now again, like the solution temperature, the thing that's really confusing is sometimes you see the temperature of the solution goes up and HCl is dissolving in water to make H plus and Cl minus ions. We come back to the idea that this is a strong acid. So in water, it's forming H plus AQ and Cl minus AQ. So the thought might be when you think about the temperature of the solution that you're touching or considering the reaction's temperature, but it's not the reaction's temperature you're touching. You're touching, like the walls of the container get hot, that's the surroundings. The thermometer gets hot, that's the surroundings. And so when the Q of the surroundings is increasing because the temperature of the surroundings went up, so temperature going up of the surroundings means the heat of the surroundings went up, must imply that the heat of the reaction dropped. And therefore, that's what we call an exothermic reaction. So negative delta H for the reaction. And the key here is what's the sign of delta H, not for the solution, but for the reaction. Honestly, I don't think we'd ever ask you for the delta H of the solution. It's a weird question, because usually we're thinking for chemical reactions. Like, what is the chemical reactions delta H? So the delta H for this reaction here, HCl gas, going to H plus aqueous plus Cl minus aqueous upon being thrown into liquid water, that this reaction here has a negative delta H. So usually when we ask you for delta H, it's almost always for a reaction. Let's see another question here that gets at a gas being absorbed. So gold can absorb hydrogen gas. This comes back to like activity series. So AuCl3 absorbs hydrogen gas. If I'm writing that as a reaction, I'm thinking of that, H2 gas goes to 2H plus 2 electron equation from the activity series. I'm thinking of the gold goes to gold 3 plus, which is lower on the chart. If you recall the chart, gold solid goes to Au3 plus 3 electrons. So I'm thinking about my activity series for this question here. And so then I have H2 gas on the, being absorbed in by the gold solution, the AuCl3 solution. And so can we form gold solid and then H plus ions? So the H plus Cl minus pair up. I should get 3 of those to use up the 3 chlorines. And then I'll need a 3 halves here, so I might then double everything. So I go 2, 3, 2, and then 6. Balancing here isn't the biggest detail. This is slightly why I wish I could have got to this point, although it would have taken so long to get here on Monday. If I could get here Monday, you can see how this kind of reviews some aspects of chapter 4 ahead of our midterm. But gold here is just undergoing this reaction that we saw in chapter 4. And we know this reaction should take place because H2 is higher on the chart, more reactive than the gold is. So we're starting with something more reactive, producing something less reactive. Okay, so now, given that we can write this reaction, think about what takes place, write the reaction. Whether or not you even have to write that reaction for this problem, I don't know. But at least it links back to something from chapter 4. But the key detail here is this is a reaction where you can see that gas is being consumed. Like that's where work comes into play, is the consumption of that gas allows us to see, well, that's the surroundings working on this system, on this reaction. So when we have the reduction in gas, so we have a loss of gas moles, that is the surroundings working on the system. That's that positive W. Like that's the W that sometimes is hard to consider. It's easy to consider a reaction that moves something because that's a combustion reaction. We do that all the time. But it's hard to consider a reaction where we have a consumption of gas. Well, here's one here. So this just leads to the consumption of gas. This is contraction. And so that should be work positive. So we're down to B and C. And then the heat change sign, I think, is pretty ordinary because it's the same one as before. The temperature increases as the reaction takes place. So the temperature of the surroundings increases, so the same thing as before. That is heat being lost by, so what's the sign of Q and W for the reaction? Heat is being lost by the reaction. So exothermic. Just like the previous page was exothermic as well, Q negative for the reaction. Okay, I think our quiz is next. So let's do our quiz and look at another slide or two, and we'll wrap up for today. Keyword for today is periodic. Periodically enjoy this class? Maybe, probably not. The word periodic just makes me think something real quick that I'll throw in here. I was looking at some of the exam results from midterm 1 and midterm 2, and the two things I was seeing that seemed to have a pretty obvious connection, I think, to doing well on the midterms was either coming to class or doing the alternate assignments. Those who have been doing those, and it's been most of the class. I mean, through midterm 1, we were at like 95% attendance. I think we're at about 90% or so, either attendance or doing the alternate assignments. So those of you that are doing the alternate assignments, that's great. I mean, there's nothing really, I think you get a great, set of tutorials, and if you watch lecture, you get just as good of an experience as if you're here, but you get a much worse experience if you don't do one of those two things, or if you don't do either one of those. If you need a little bit more from lecture, maybe check out the tutorials, even if you're coming, maybe they're helpful. It won't hurt you to check them out. Reading the book is helpful. That's why I go kind of light on the homework, is because I really like to encourage just like after class, just try to read through, connect the ideas, look at some simple problems. You get the reward if you do read the book, and that those problems are more or less the post-lecture problems, because I really think that's where the greatest attention can be. If that's in the form of tutorials guiding you through it, if it's in terms of reading the book, really, really helpful. But then the last thing was the practice exams. I mean, if the difference between not having done the practice exams and doing at least one of them was like about a 20% difference in midterm score. But I think it's also, if you're not valuing coming to class and doing the homework, that's probably a lot of common features, not necessarily not doing them, that lead to a low score too. But just try to be as motivated as you can. I know it's hard, like you guys are here the day after a midterm, so that's great. If you're catching this, tonight on video, that's great too. Just try to keep up. Like that's the hardest part of college, is like we don't stop. Just because we take a test doesn't mean we take a day off. We get right back to it. And that makes it hard from your end, because sometimes you really just want to take a week off. Just try to fight that urge as best as you can, just to stay on track for this class, all your classes. You miss a couple classes, get behind, things get really hard. If you just stay periodic, stay on track, things kind of fall into place a lot easier. Okay, so the word periodic made me want to go into that detour, so we went there. Okay, let's look at then enthalpies of reaction and start throwing some numbers onto these things, because our units are going to be primarily in kilojoules, is the main unit of energy that we use the most. The SI unit of energy is the joule. Kilojoules of obviously just 1,000 joules. And again, delta H is just the idea of whatever the enthalpy of the products, like we'll see later that it's like the sum of the enthalpies of the products minus the sum of the enthalpies of the reactants. That's what delta H is. So it's the change of the enthalpy during the course of the reaction. I don't always write delta H reaction, but if I write delta H, it's like the idea is it's the enthalpy change of the reaction. And so delta H is extensive. What that means, it's quantity dependent. Now it's quantity dependent because we don't write the per mole in. So when we have like water liquid going to water gas, that's the vaporization of water, that's like boiling water. So we can also think about the physical sign that should have. So we can kind of connect some ideas here too on if you have liquid water, you want to vaporize it, you got to put heat in. So the water has to absorb heat to break its bonds, break those intermolecular forces of attraction. So of course this would be endothermic. I think that makes a lot of sense for phase change. For some reactions, you can get a mental picture of should it be exothermic or endothermic. And so for water vaporizing, that's endothermic, heat has to be absorbed. So if we have 1 mole, now our delta H is assuming that the coefficients are moles. So this is assuming you have 1 mole of water turning into 1 mole of product. And so this delta H here assumes the coefficients in the reaction are moles. So like 1 mole of water liquid to 1 mole of water gas, that's 44.0 kJs. Now the extensive nature is that if I double the quantity, then I need to double the magnitude of my delta H. So if I put 2 in front of water, now I'm assuming that's 2 moles of liquid water. I have double the volume. I'm going to have to absorb then double the amount of heat to boil. So delta H is quantity dependent, so that's 2 times the 44.0. And just notice that we don't write per mole. So the reason why this is that it's like kilojoules, and it assumes, and sometimes we call this the reaction is like assume per mole of the reaction or per quantity of the reaction is indicated by its coefficients. So you don't see a per mole written here. That's because we're assuming the coefficients are the moles in the reaction. So the minus 44.0 is kJs per like 1 mole of liquid water, and the 88.0 is per 2 moles of liquid water. So the ratio in terms of kJs per mole of water is a constant, but we leave the mole off of our reactions. Now, if you flip the reaction, then you better flip the sign, otherwise we're creating and destroying energy. So if you flip the reaction to water, gas to liquid, if you have gaseous water condensing, then you can get energy out of that process. You can get enthalpy out of that. That has a exothermic sign, a negative delta H. And of course, it's negative 44.0. It's the opposite of whatever the sign for the forward reaction was. So flip a reaction, you just change the sign to negative for the delta H. And then delta H depends on the physical states of the substances. So like I see here, methane plus 2O2 goes to CO2 plus water liquid. That has a delta H of minus 890 kilojoules. And then if I note that earlier, we saw that the liquid water to gaseous water was 88.0. If I add these 2 reactions up, then my water liquids on both sides. So if I add the reactions up, I can simply sum up their delta H's. And so that'll be minus 802 kJs is then the reaction for methane plus oxygen, 2 oxygens going to CO2 plus 2 water, but now gas phase, gaseous water. So the delta H's depend on the physical states of the reactants. If you change a liquid to a gas, you would change the magnitude of delta H accordingly. And then here we can even do a little summation. This summation addition here is a like preview of Hess's law. This is Hess's law in action. We'll see that as a topic defined a little bit more in a couple of slides from now, maybe Friday, if not into Monday's lecture. But we see there just adding reactions up, we add up their delta H's, but also seeing that delta H depends on the physical states of the reactants and products. I'm just gonna peek here. We'll save this problem for Friday. We'll start with a problem using delta H next time. So that'll do it for today. I'll see you guys on Friday.